Let's suppose that we have a body with mass capital M and another body with mass little m. The gravitational force F between the two bodies, we know that the length of that force is proportional to the product of the masses times a constant over the distance between the two bodies square. Here we're going to assume that R1 is x1, y1, and R2 is equal to x2, y2. We have that mass times acceleration is equal to negative f, and this mass times the acceleration of the body, which is R1, is equal to the force. Then here we need to solve the two-body problem. We need to find four functions: x1 of t, x2 of t, y1 of t, y2 of t. That satisfies this differential equation. A solution that maybe is the easiest solution is the one in which the two bodies move in a circle. This is the body with mass m moves in this circle, and the other body with mass little m moves in a circle also. This radius is R2, this radius is R1. The connection between R2 and R1 is that R2 is capital M over little m times R1. And this motion has the property that if the body with mass m is here, the other body is diagonally opposed to that one, then it is going to be here. More concretely, we can say that R1 is equal to negative R1. That is that R1 is a vector, and little R1 without the vector is just the number, the radius. Cosine of kt, sine of kt, and R2 is R2 cosine of kt, sine of kt. Then we can check that these four functions, x1, y1, x2, and y2, they satisfy this differential equation. Notice that the distance between the two bodies is always the same, is R1 plus R2. Also, you can check that they solve the differential equation if the relation between the radius is this, and the angular frequency satisfies this equation. Angular frequency squared is equal to the sum of the masses times the gravitational constant over the distance between the two bodies to the power of 3. Then we have, this is called the circular solution of the two-body problem. We're going to assume that we have this solution, which is the easiest one, and even though it's the easiest one, it's very important because most of the planets is in our solar system, they have a solution very similar to this one. They move on ellipses, but those ellipses, the eccentricity is so close to zero that a good approximation is a circle. Then we're going to assume that we have a body here with mass m3, and we're going to assume that this mass doesn't have to be small, but it is such that it doesn't affect the motion of the other two bodies. We're going to call these bodies the primary bodies. Let's call this primary body 1, primary body 2. And then let's see what is the equation for this body with mass m3. We have a force here F1, and we have another force due to the gravitational force going in that direction, F2. Then M3 times the acceleration. Let's suppose that this body, it has these coordinates. Vector r is x of t, y of t. Remember, we are using x1 and y1 to be these two. Sorry, x1 and y1 are these two, x2 and y2 are these two, and my x and y are the unknown, and they describe the motion of this body. And then we have that mass times acceleration must be equal to F1. F1 is negative m3 times mass capital M over g over the difference, the distance between the two, which is this, q times r minus r1 plus, minus m3 times little m, which is the mass of this body, times the gravitational force over r minus r2 cubed times the vector r minus r2. Okay, one important observation is that m3 you can cancel m3 from this equation. Then that means that the equation, the differential equation that describes this motion is independent of the mass m3. Then we want to solve this differential equation. We are looking for two functions, x of t and y of t, that satisfies this differential equation. One of the properties of this differential equation is that the time t appears explicitly here. This expression here has a t explicitly, and for that reason this differential equation is what is called a non-autonomous differential equation. Okay, in order to study this motion, it's better to do a change of variable. The change of variable that we're going to do is we're going to change the system of reference so that our c-axis is this. This is the c-axis, and this is the w-axis. And then we're going to be thinking about two functions, c of t and w of t. Essentially what we are assuming is that our observer is rotating so that this observer is located at the center of the two circles and is always looking at this body, at this primary body with mass m, little m, right? The observer is rotating, and then since the observer is rotating in this system of coordinates, this body, primary body, is always constant in that system of coordinates. The connection between the two coordinates is the following. We have that x and y is equal to c cosine of kt sine of kt plus w negative sine of kt cosine of kt. Notice that when we think about these coordinates, r2, 0, that means that c is r, w is 0, and when you make this equal 0, then essentially you get this coordinate. You get the coordinate, you get the motion of this primary body with mass little m. And the coordinates for this one in the CW coordinates would be negative r1, 0. And then we can change, we can use this differential equation, use this relation to find the differential equation that C and W of t satisfies. We have the following. Here we have our C and W. In this system of coordinates, we have that here is this primary body, here R2, and this is R1, and we have our C and W here. And then for any C and W, I'm going to call this distance from here to here. I'm going to call that distance D2, and this distance D1. Then the differential equation that you get by using this connection, this relation, and using this differential equation is the following. We have that C double prime is equal to K squared times C plus K times W prime minus C plus R1 times M times G over D1 cube minus C minus R2 times little m times G over D2 cube. And W, the second derivative of W is K squared times W plus minus K C prime minus W times M times G over D1 cube minus W times M times G over D2 cube. Then we have this system of differential equations that represents the solution of the x and y, which is a body that moves under the effect of the gravity of two bodies that move in a circle. Okay, then we are going to be interested in finding out initial conditions, let's say C of 0 and W of 0, C prime of 0 and W prime of 0, with the property that after some time t, we have that this is equal to C of t, this is equal to C prime at that time, this is equal to W prime at that time, and this is W at that time. Then we are interested in orbits that are periodic, with period capital T. But before studying those orbits, we are going to define a function that helps us to do that study. I forgot to mention that one of the properties that make this differential equation a little easier than this one is that here the t is not explicitly in the differential equation. Even though we are looking for W of t and C of t, the t is implicitly in the functions, but it's not explicitly in the differential equation, and for that reason this system is an autonomous system. Actually, we can try to find the equilibrium solutions. We can try to find solutions such that this is a constant and this is another constant. If you want to look for solutions in which the C is fixed and the W is fixed, then the derivative, these derivatives cancel out. This is 0, this is 0, and you end up solving this equation, K squared times C equals to this part here, or this equals to that part here. There is a minus that you can move to the left. When you solve, you can solve that equation and you end up with a solution like this. Here is negative R1, here is R2, and when you solve the equation, let me just write the equation that you need to solve to find equilibrium solutions, to find solutions in which C of t is constant and W of t is constant. You have to solve this equation. Then you can see that there are 5 solutions for this system 2 by 2, and there is one solution here, another solution somewhere here, another solution here, and there is a solution that it forms an equilateral triangle with these two. Here is, this one is called L4 and this one is called L5. Okay, then let's continue with the differential equation. We are going to find a relation between this period, right, of an orbit, of a periodic orbit, with this region here, omega. Okay, let me rewrite this differential equation. We notice that algebraic verification shows that if I define h to be equal to 1/2 k squared c squared plus w squared plus mg over d1 plus mg over d2, then this differential equation can be written in this way: c prime equal the partial derivative of h with respect to c plus k w prime, and w prime equal the partial derivative of h with respect to w minus k times c prime. Another important observation is that if we take any solution, it doesn't have to be periodic. If we have here c and w, and we have some initial conditions, and then we have a solution of this differential equation, a solution c of t and w of t, then when you compute c prime of t and w prime of t, which is the velocity, for any t, it doesn't matter what t is, when you evaluate 2 times h, right? H depends on c and w, and then here you replace c of t and w t. This is an expression in terms of t minus c prime squared plus w prime squared. You can check that this is always the same. This is a constant c that is independent of the t. This is a conservation property, a first integral, like conservation of, something like the conservation of energy. Then we have this property, and the proof is relatively easy. You just take derivatives with respect to t, and then you use this differential equation, and you can show that this part, the derivative of this part, is 0. And for that reason, it must be a constant independent of t. Okay, then we have that. Notice that this function h is defined everywhere except at these 2 points, negative r2 and r1. Also, if we have a solution like this, if we define our function f to be a square root of 2h minus c, then we know that this f for any solution, c prime y prime, the norm of this vector, is going to be f of c of t w of t. We have this property. Okay, the main theorem says that if you have a closed orbit, something like this, and let's suppose that that orbit is moving clockwise, and let's suppose that it encloses a region omega. Then what the theorem says is that 2 times k times the period is going to be equal to 2 pi plus the integral over that region of the Laplacian of natural log of f. We have this is in the case in which the orbit moves clockwise. If the orbit moves counterclockwise, then we have that 2kt is equal to negative 2 pi minus the integral of omega of the Laplacian of natural log of f. In the case that the orbit goes around this point, notice that the function f is not defined at that point, but something that you can prove is that even though the function f is not defined at that point, you can still compute this integral. And what you can show in this case is that if the orbit goes clockwise, then we have the 2k times the period. Remember that the period is the time that it takes to come back to the same point in these coordinates. Right? We have that c of 0 equals c of t, c prime of 0 equals c prime of t, w0 equal w of t, and w prime of 0 equal w prime of t. This is the t that I'm referring here. 2k times t, this is equal to just pi. The only thing that changes is that this 2 pi changes to pi. And in the other case, when the orbit goes counterclockwise, we have 2kt equal negative pi minus the integral of omega of natural log of Laplacian of f. Also, the last theorem, the last part, if the orbit goes around these 2 points, then the theorem says that 2kt is just the integral over Laplacian of natural log of f. This is if it goes clockwise, and if it goes counterclockwise, then we have 2k pi, 2k the period equal to negative the integral of the Laplacian of natural log of f. Okay. In terms of the proof of the theorem, essentially the proof of the theorem, it follows from the fundamental theorem of calculus. What we can do, using this observation, we know that c prime is equal to f cosine of some function theta of t, and w prime is f sine of some function theta of t, right? Because the norm of the velocity is equal to f. Then, using the differential equation for c and w, we can compute theta prime, and then we can compute that theta prime is equal to negative 2k plus partial derivative of h with respect to, partial derivative of f with respect to w times cosine of theta minus partial derivative of f with respect to c sine of theta. And then by using the fundamental theorem of calculus that says that the integral from 0 to t is of theta prime of t dt is equal to theta of t minus theta of 0, which is, this is going to be either plus or minus 2 pi, depending of if it goes clockwise or counterclockwise. Using this theorem and using the fundamental theorem of calculus for two variables for regions in the plane, which is called the Green's theorem or the Stokes theorem or the divergence theorem. Essentially, it says that the integral over omega of the Laplacian of a function, that this integral is just the integral over the boundary of the gradient of natural log of f, that a normal vector. In this case, we have the closed orbit. This is omega, and here is the normal vector that points outside of the region. Then these two theorems, or these two observations, combined with this formula, just provide the whole theorem here. Okay, this is it for this video.